Welcome to The Explainer. Today, we're unpacking a complex but absolutely fascinating engineering challenge that is literally reshaping our electrical grids as we speak, demystifying GFM inverter integration in legacy BSES. If you're curious about how the backbone of our modern power systems actually functions, and you really want to understand the massive technical hurdles that system engineers are racing to solve right now, well, you're in exactly the right place.
I want to pause for a second and talk directly to the power system engineers and grid operators tuning in. Have you encountered unexpected stability or control conflicts when integrating grid-forming assets into legacy multi-inverter environments? I bet a lot of you are nodding your heads right now, feeling those real-world operational frustrations. It is a massive headache in the field today. Okay, let's dive into this because understanding exactly why this happens is the key to unlocking the future of our energy transition. Here is our roadmap for today. 1. The grid-forming mandate. 2. The plug-and-play myth. 3. Anatomy of inverter clashes. 4. Upgrade or over-engineering. And 5. Strategies for seamless deployment.
Section 1. The grid-forming mandate. From theoretical to mandatory.
Not too long ago, grid-forming technology was really just a theoretical concept tossed around in grid code meetings. Fun fact, just 5 years ago, finding a mandatory GFM requirement was kind of like finding a needle in a haystack. But today, GFM inverters are quickly transitioning to mandatory assets required for stabilizing weak networks. We're way past the days of just meeting basic compliance checkboxes. As legacy networks become more fragile during this energy transition, these assets are absolute necessities to keep things stable. But adding them to what we already have built out there, well, that's exactly where the friction begins.
Section 2. The plug-and-play myth, when operating languages clash.
You know, there's this pervasive industry myth that retrofitting new GFM inverters into existing grid-following utility-scale parks is just a simple plug-and-play process. You just plug them in, turn them on, and they play nice, right? Well, not exactly. And this brilliantly illustrates why. On one side, you have voltage source devices. These are your new GFM inverters. On the other side, you have current source dynamics, which define your legacy battery energy storage systems, or BESS environments. Dropping a voltage source device into a system engineered from the ground up for current source dynamics creates a literal, physical clash between two entirely opposed electrical languages. You're forcing two complex systems to communicate, but they speak completely different dialects.
Section 3. Anatomy of inverter clashes. The friction points. Before we get into the specific challenges, we really need to understand one absolutely critical concept: harmonic resonance. What is it? It is the unexpected multi-inverter instability that surfaces when dropping voltage source devices into current source environments. Think of it like multiple musicians in a highly coordinated orchestra who suddenly decide to play in completely different tempos, in completely different keys. That destructive, chaotic noise is exactly what harmonic resonance looks like inside a power system. It's highly unpredictable, it's deeply destabilizing, and quite frankly, it's a massive risk. But harmonic resonance is just one piece of a very complex puzzle. So the crucial point is, the harsh reality of these unexpected operational failures really boils down to 3 stability friction points: control loop interactions, phase angle synchronization hurdles, and those harmonic resonance risks. When legacy and new inverters try to command the grid simultaneously, their control loops essentially fight one another. On top of that, getting their complex phase angles perfectly synchronized is an immense mathematical and physical hurdle. And when these dynamics go wrong, system reliability just drops entirely.
Section 4. Upgrade or over-engineering, the great industry debate.
This technical friction has brought engineers to a massive crossroads, sparking a pretty high-stakes debate. The central question being asked is this: are we deploying precise architectural upgrades or engaging in expensive over-engineering to compensate for lagging transmission infrastructure? One camp views integrating these complex GFM assets as a totally necessary architectural upgrade to modernize our grid. The other camp views it quite differently, arguing that we're really just throwing highly complex, expensive inverter technology at a fundamental physical problem, which is lagging transmission lines. It's a fascinating debate about where capital, time, and engineering resources should truly be directed, and the industry is still figuring it out.
Section 5. Strategies for seamless deployment. The engineering roadmap.
Regardless of where you stand on that debate, these deployments are moving forward fast. To ensure they happen without triggering those unintended operational failures, we have to implement 3 essential system engineering strategies.
Step 1. Manage control loop interactions. You cannot leave this to chance. The logic between old and new systems must be intentionally coordinated. Step 2. Synchronize complex phase angles. This takes rigorous pre-deployment modeling to ensure the voltage and current source devices are entirely aligned before you even flip a switch. And Step 3. Mitigate multi-inverter resonance. This means engineering robust damping mechanisms directly into the system so that when those resonances try to surface, the overall system absorbs them without sacrificing an ounce of reliability. So that leaves us with one final, critical thought to ponder. Will your next GFM integration trigger an unexpected failure, or will it achieve seamless stability? By really understanding the fundamental clash of these electrical languages, anticipating the harmonic resonance risks, and applying strict engineering strategies, you have the blueprint to successfully stabilize our weak networks. Thank you so much for exploring this highly technical, fascinating topic with me today. Take these insights back to your own legacy systems, keep pushing the boundaries of grid reliability, and I'll see you on the next explainer.